Question number 8. Before Einstein won the Nobel Prize for discovering the photoelectric effect, classical physics suggested that there is no minima of energy needed to eject electrons from a metal. Explain the principles of the photoelectric effect and how Einstein concluded that light is particle-like. So I'm going to start by drawing a diagram first. So pretend that this is a metal surface, and there are electrons. And then we shine a light. We can call this the incident light. And then electrons may or may not be ejected. So I'll explain when electrons won't or will be ejected. So we have to remember that light is made up of particles. These particles are what we call photons, and the photons are made out of quanta of energy. Now, this energy is then related to the frequency of the radiation. So energy of the photon is equal to Planck's constant times the frequency, or Planck's constant times the speed of light over the wavelength. So it's also related to the wavelength. Now, the metal, it has something called a work function, and it's usually given a symbol like this, work function. Now the work function is defined as the minimum energy needed to remove an electron from the solid. So it's equal to Planck's constant times a minimum threshold frequency. So this is the minimum frequency of the photon required to produce a photoelectric emission. So in order for electrons to be ejected, the energy of the photon must be greater than or equal to the work function. For different metals, they have different work functions. Now, if the energy of the photon is greater than the work function, then the electron will be ejected with some kinetic energy. Now, if the energy of the photon is not greater than the work function, then no electrons will be ejected no matter what. No matter how long you shine the light on the metal, if the energy is not enough, the electrons will not be ejected no matter what. This is an important concept. If the energy is not greater than the work function, then electrons will not be ejected.